Welcome to part 2 on finding the nth roots of a complex or real number. In this one, I'm going to find all the roots of a complex number. In the part 1, I did it of a real number. Finding all the nth roots of a complex number is a little bit more difficult, but not much. Again, involves a lot of the same ideas. I would suggest watching part 1 before part 2. But again, we're going to be using my little step-by-step tutorial for finding the nth roots. So write the number. Step 1 is write the number as a complex number in polar form. Step 2, find one root by raising it to the 1 over n power and using DeMoivre's theorem. And I just realized I misspelled theorem here. That's a little embarrassing, but a little mistake there. But DeMoivre's is not actually misspelled. And then step 3 be repeatedly adding 360 over n to find the other one. So gonna do it a little bit faster this time. So start off by rewriting our number z is equal to negative 8 plus 8 root 3i. And we're going to rewrite that in polar form. So in order to do that, we need to know what is the r and what is the theta value. So again, you could graph that number and use geometry and trigonometry to figure out what what angle this is at and what the radius, what the distance from the origin to this number in the complex plane would be. But as I showed you in class, there's a little quick, easy way to do it using your calculator, and so that's how I'm going to do it in the tutorial. Basically, if we want to find r and theta for this complex number, we can use there's complex math in our calculator. If we go to math, scroll over to CPX, that's where the complex math is. If we go down to number 5, the absolute value, if we type into our calculator the absolute value of negative 8 plus 8 rad 3i, basically what our calculator is going to do is it's going to calculate, well, what is the distance from the origin to this complex number in the complex plane. That's kind of what the absolute value means. So luckily our calculator will find the absolute value of this. So that tells us that r is equal to 16. And so for polar form, we also need to know what is theta for this number. So similarly, we could use what's called, if we go again back to math, scroll over to CPX and go down to angle. Again, what we'll do is our calculator will find the angle of this complex number. What angle is this at in the complex plane as well? So we simply just type all that in. You could also use a tangent or a cosine, arc cosine function to find it, and Pythagorean theorem to find r. But I find this is just a little bit faster. So we get kind of this result, 2.094. Which, if I examine this complex number in the complex plane, that's going to be in quadrant 2 because x is negative and y is positive. So this coordinate would be in quadrant 2. Obviously this is not a degree answer. This is probably in radians. In the last tutorial, I like to do it in degrees. Typically, I like to use degrees because it's a little bit easier to use a calculator, a little bit easier for the common person to understand. But if we change our calculator to degree mode and reevaluate the angle of our complex number, we see that 2.094 in radians is actually at 120 degrees. So what this value was actually 2 pi over 3. So if you wanted to do this in radians, you could just use 2 pi over 3. Double check. Yes, 2 pi over 3 is exactly the same as that angle. So we're at the angle theta is equal to, again, if we're in radians, we would do 2 pi over 3. But if we're in degrees, we would do 120. And again, I like to do degrees. I just find it a little bit easier to graph and stuff. We don't have to do all the relations between. It's good to know your radian mode, of course, as we talk about. But just for these problems, I like to use degree mode. If you are using Euler's formula and using the form e to the I theta, you cannot use degrees though. So strictly for using cosine plus sine, this will work. But the reason probably why your textbook uses radian mode, never degree mode, is because if you ever take complex analysis and you do it the other way, degrees will no longer work. But that's something that you guys should know the connection between degrees and radians at this point. So anyways, back to the problem. We rewrite our number if we're trying to find the 4/4 roots of negative 8 plus 8 rad 3i. We rewrite it in polar form, so simply that's 16 CIS of 120. And again, we found those values by using the two functions ABS, the absolute value, to find 16, and angle to find the theta, the argument of the polar number. So what we do next is, now that we have it in polar form, we take the nth root of it, or we raise it to the 1 over n power. And then we're going to use DeMoivre's theorem to simplify. So just like in the last example, we take this and take this whole number, 16 CIS 120. And in this case, since we want to find the 4 fourth roots, we raise it to the 1/4 power, basically. So we're going to find z raised to the 1/4 power, and that's going to be equal to 16 to the 1/4 power. And again, if we raise CIS 120 to the 1/4 power, that changes to a multiplier. We get CIS 1/4 multiplied by 120 degrees. And so what that would get us, well, 16, the fourth root of 16 is 2. And for 1/4 times 120, 1/4 of 120 is just going to leave us with 30 degrees. And so we're going to have 2 CIS, 30 degrees. And then this will be our first solution, our first root. So this is going to be number 1. And then we find the other ones. In this case, we need to find 3 more by repeatedly adding. Well, and it's always 360 over n. In this case, we're adding 360 over 4. N is the index, or 4, because we're finding the fourth root. So we're going to repeatedly add 360 over 4, which is 90 degrees. So we're going to take our argument, repeatedly add 90 degrees in this case, to find the other one. So for number 2, I'm just going to kind of write them like this so I can keep track of all my roots. But the first one is going to be, we're going to add 90, so we're going to have CIS 120 if we add 90. And then if we add another 90, we're going to get 210 degrees. And then if we add another 90 to that, we're going to get 280 degrees. And that, what did I just, no, sorry. 210 plus 90 is not 280. I don't know what I was thinking there. But of course 210 plus 90 is 300, so let me get rid of that. Something was going wrong in my head. It's like, that doesn't seem right to me, because obviously it's not. So sorry, a little mistake on my part. Of course 210 plus 90 is 300. And so there we have our 4 fourth roots of negative 8 plus 8 rad 3i. So, of course, now let's put them back into rectangular form, because it's always nice to rewrite it, because normally most people are used to dealing with complex numbers in rectangular form, not in this polar form. So if we go back to the normal form, then more people will understand our solution. So let's go take these things and return them to rectangular form. So starting with 2 CIS 30. Let me just rewrite all my roots. We had 2 CIS 30 was the first one. 2 CIS 120 was the second. Then 210. And then finally, the last one was 2 CIS 300, not 280. So we're going to take all these guys, now expand them. So cosine plus I sine theta, just like in the last one, that's our abbreviation for cosine plus I sine theta. So cosine of 30 degrees, pulling back up my unit circle here. Cosine of 30 degrees would be root 3 over 2 plus I. And sine of 30 degrees is over here, 1/2. Again, you should have your unit circle memorized. Hopefully you should be able to do this without a unit circle by now, but I like to continue to use it just to reinforce how we figure those out. Okay, 120, we're having cosine and sine, so we do 2 times cosine of 120. Cosine of 120 is negative 1/2 plus I times sine of 120, which is root 3 over 2. The third complex root, changing it back, would be cosine of 210 plus I sine of 210 times 2. And so, again, those are going to be the same values at 30 degrees, but negative. So down here at 210 degrees, we have x is negative rad 3 over 2 plus I times negative 1/2. And then our fourth root of 16. Again, back to the original sorry, not 16 of our original number was negative 8 plus 8 rad 3I, but in polar form it was 16 CIS 30. So it's not of 16, it's of the original number. So don't forget what we're doing in this problem. But going back, so finally our fourth root will be 2 times CIS 300. 300 is over here. So cosine will be 1/2 and sine would be negative root 3 over 2. So finally we'd have positive 1/2 for cosine plus I times negative rad 3 over 2 for the sine of 300. And these would be all of our roots. And again, back to the original number was this. We're finding the fourth roots of negative 8 plus 8 rad 3I. And so again, what this means is that those four numbers, if we raise them to the fourth power, should return us to this number. So all four of these should, when raised to the fourth power, get back there. And if we do just some quick distributing here, 2 divided by 2 would make 1. So 2 times rad 3 over 2 would just make rad 3. And 2 times 1/2 would just make 1. So we get 1I, or 3 plus I. And if we distribute the 2 here, again, the 2 would cancel both denominators. We'd be left with negative 1 plus rad 3I. Then this one, if we distribute the 2 times negative rad 3 over 2 would be negative rad 3. And then 2 times negative 1/2 would be negative 1, so negative 1I. So let me actually erase that. I want plus 3, negative root 3 minus, so sorry, 2 times I times negative 1/2 should be 2 times negative 1/2 is negative 1 times I, so just negative I. Again, notice that this one, this third root and the first root are conjugates, which, as I mentioned in the last video, should happen. Sorry, they're not conjugates. As I mentioned in the first video, if you're dealing with a real number with real roots and real polynomials, conjugates should always be a part of it. But if you're dealing with complex numbers and complex roots of complex numbers, they won't always necessarily be conjugates of one another. So notice these are actually not conjugates. They look kind of like conjugates at first, and that's what tripped me up initially. But the first one is root 3 plus I, and the next one is negative root 3 minus I, which is not a true conjugate. A true conjugate should have the same real component and opposite sign on the imaginary component. So in this case, our real component has opposite sign, so it's not a true conjugate. But okay, on to the last one. 2 times 1/2 is 1. 2 times negative rad 3 over 2 is negative rad 3 times I. Again, which is almost a conjugate, not quite. And so there we have it. Those four numbers are the fourth roots of our original number. So let's lastly just check this out with our calculator to make sure it. Why I like to do this is I like to see that it all makes sense, because it can seem very abstract what we're doing if we don't really understand what it is we're looking at. But basically, we want to figure out what are the fourth roots of this number. So we want the numbers that, when raised to the fourth power, you repeatedly multiply them 4 times, give us this. And so going to our calculator, it's going to be not too hard to check these with the calculator. So if we're looking at this, let's just see. Our original number is negative 8 plus 8 rad 3I. I'm just going to rewrite this as a decimal so that we can check this out, make sure it's the right thing. So that's about negative 8 plus 13.856I. So essentially, if we take all four of these numbers and raise them to the fourth power, that should give us our original number. So we take the cube root of 3 plus I. And so if we take this number and multiply it by itself 4 times, we should get our original number, which, cool, works. So again, if you do it by hand, it would take you a little bit of time and work to get there, but should work as well to take root 3 plus I, repeatedly multiply it to itself 4 times, should come up with this as well. But anyways, we take the next one, negative 1 plus rad 3I. And if we raise this to the fourth power, should also give us the same number. So good, so far so good. Let's try the next two, make sure they work as well. So negative root 3 negative square root of 3 minus I. And if we take that to the fourth power, cool. And the last one, maybe, let's just go ahead and do it since we're already there. 1 minus, maybe you could just take my word for the last one. But as usual, you should never just trust me. You should play around with things for yourself. Try some of these problems, similar problems on your own. And so we get the same answer as well. So there we have it. We can conclusively say we found the fourth roots of negative 8 plus 8 rad 3i by using polar form of complex numbers in DeMoivre's theorem. So again, pretty fun little theorem. I really enjoy it. Think it's fun. It ties a lot of algebra in complex math. And again, you'll study this stuff more in depth if you ever take a course in complex analysis. But for the sake of our pre-calculus class, this is kind of far enough a good little introduction into complex numbers and some of the more fun aspects. And I really enjoy complex numbers. Hope you guys do too. So happy studying. Let me know if you have any questions. Feel free to leave comments. Throw me a like if you don't, or if you have any suggestions how I can improve these videos. Again, feel free to let me know. Constructive criticism is always appreciated. Have a great day. Bye.